Hello friends, welcome you all to the 18th lectures on functional analysis and its applications. In this lecture, we will discuss the linear functionals, dual vector space and dual basis. These are the contents of today's lecture: linear functionals, dual vector space and dual basis. Linear functionals. Definition: let L be a linear space over the field F. A linear functional on L is a linear map F such that L to F, such that f of x plus y is equal to f of x plus f of y for all xy belonging to L, and f of ax is equal to a f x for all a belonging to F and x belonging to L. Equivalently, these two conditions can be written as f of ax plus by equal to a fx plus b fy for all ab belonging to F, that is scalar, and xy belonging to L, that is xy is vector. If f is linear functional on vector space L, then fx is the element of F. Okay, x belonging to L, then fx is the element of F for all x belonging to L. Since fx is scalar, therefore linear functional on L is scalar valued function. For example, let vector space L is equal to C01. C01 means set of all continuous linear function under the closed interval 0 to 1. Then for xt belonging to C01, function xt is the element of C01. Define fx is equal to integral 0 to 1 xt dt is linear functional on C01. Solution: for if x1 and x2, two functions belonging to C01, we have, as per the statement, we can write f of x1 plus x2 is equal to 0 to 1 x1 plus x2 t dt. Okay, then it can be written as x1t plus x2t dt. Okay, equal to 0 to 1 x1t dt plus 0 to 1 x2 dt. That is, as per the statement, this can be written as f of x1 and this can be written as f of x2. And also, if a is scalar, then f of ax is equal to 0 to 1. This can be written as 0 to 1 ax t dt equal to 0 to 1 a into xt dt. And this can be written as a into 0 to 1 xt dt. Okay, a is outside the integral because a is independent from t. So a 0 to 1 xt dt can be written as a into f of x. Okay. Next example. Let Fn be the linear space of all ordered n tuples of the elements of the field F. Let alpha 1, alpha 2 and so on alpha n be n fixed elements of field F. If x is equal to n tuples of x1, x2 and so on xn is the element of vector space Fn, we define Fx, that is f of x1, x2 and so on xn is equal to summation I is equal to 1 to n alpha I xi, that is alpha over x1 plus alpha to x2 plus and so on alpha n xn. Then f is linear functional from Fn to f, and alpha I is f of ei, where I is equal to 1 to n, where ei, suppose e1 means n tuples of 1 0 0 up to 0 n time, okay, and e2 0 1 0 dot 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 0, these are n tuples. Similarly en 0 0 dot 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 1, n after 1 is the standard basis for vector space Fn. Proof. Let x equal to n tuples of x1, x2 and so on xn, and y is equal to y1, y2 and so on yn, and if AB belonging to F, that is scalar, we have f of ax plus by. Here vector ax plus by, so it can be written as value of x here, x is x1, x2 and so on xn, and y is y1, y2 and so on yn, okay. Then f of a value of x, x1, x2 and so on xn, plus b value of y, y1, y2 and so on yn. This can be written as f ax1, ax2 and so on axn plus n tuples of b y1, b y2 and so on b yn equal to, here this is the sum of two n tuples, okay. So it can be written as f of ax1 plus by1, second ax2 plus by2 and so on axn plus byn, okay. So as per the statement, so here we have n tuples ax1 plus by1, ax2 plus by2 and so on axn plus byn. So we can write this alpha 1 ax1 plus by1, alpha 2 ax2 plus by2 plus and so on alpha n axn plus byn, okay. Here after multiplication of alpha 1, alpha 2 and so on alpha n, we can write a alpha 1 x1 plus b alpha 1 y1 plus a alpha 2 x2 plus b alpha 2 y2 plus and so on. And this can be written as a alpha 1 x1 plus this term a alpha 2 x2 plus and so on this term a alpha n xn as one term plus second term b alpha 1 y1 plus b alpha 2 y2 plus and so on b alpha n yn, okay. So common a in first term and b common from second term. So we can write A into alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn plus B alpha 1 y1 plus alpha 2 y2 plus and so on alpha n yn. That is this one as f of x1 x2 and so on xn, and this term can be written as f of y1 y2 and so on yn. That is this term can be written as a f of x plus b f of y. So f of ax plus by is equal to a fx plus b fy. Therefore, f is linear functional on Fn. Remark. Converse of the above example, for any given linear functional f on Fn, consider alpha I is equal to f of ei. Then for any vector x is equal to x1 e1 plus x2 e2 plus and so on xn en belonging to Fn, we have fx is equal to summation I is equal to 1 to n xi f of ei. F of ei, that is alpha I, that is summation I is equal to 1 to n alpha I xi. Noting point: if f is linear functional on a linear space L over the field F, then f is a linear transformation from L into the linear space F. Therefore, f will possess all properties of the linear transformation. Okay, so linear functional very close to linear transformation. Dual space. Let L be a linear space over the field F, then dual space of L denoted by L star or L dash is the set of all linear functional from L to F. Okay, L and F both are vector spaces over the same field F. Okay, so linear functional from vector space L to field F. Okay, that is L star is equal to beta LF. Beta LF is a notation of the set of all bounded linear functional. Okay, defined as F such that L F to FF. That is map F such that L to F over the same field F, where F is linear. Okay. Suppose F1 and F2 belonging to L star, that is dual space. That is F1, F2 are linear functional on L. Let us define the mapping F1 plus F2 by F1 plus F2x equal to F1x plus F2x for all x belonging to L. Also, if A is scalar and F is the element of L star, let us define the mapping AF by AFX equal to A into Fx for all x belonging to L. Noting point: both F1 plus F2 and AF are linear functional on L. Also, for these linear operations, L star is linear space over the field F. So we can prove easily. So proof of this is a linear space over the field F, omitting. Theorem. Let LF be an n-dimensional linear space and B x1, x2 and so on xn be an ordered basis for L if gamma 1, gamma 2 and so on gamma n is any ordered set of n scalars, then there exists a unique linear functional on L such that fxi is equal to gamma I. Okay, where I is equal to 1 to n. That is f of x1 is equal to gamma 1, f of x2 is equal to gamma 2, and so on f of xn is equal to gamma n. Existence of f. Let x is the element of L. Since B is a basis for L, therefore there exists unique scalars alpha 1, alpha 2 and so on alpha n such that x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. For this vector x, let us define fx is equal to f of alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. So f is linear functional, so it can be written as alpha 1 f of x1 plus alpha 2 f of x2 plus and so on alpha n f of xn. Okay, because here alpha 1, alpha 2 and so on are scalar, and x1, x2 and so on xn are vectors. Okay, so we can write this. And here f of xi is equal to gamma I. So f x1 can be written as gamma 1, f x2 can be written as gamma 2 and so on, f xn as gamma n. That is f of x is equal to alpha 1 gamma 1 plus alpha 2 gamma 2 plus and so on alpha n gamma n. Obviously, fx is defined by us here is unique element of f. Okay, because here gamma 1, gamma 2 and so on gamma n all are scalars. Alpha 1, alpha 2 and so on alpha n also scalars. So these sum also scalar. So fx as a scalar. So fx defined by us is unique element of f. Therefore, f is a mapping from L into f. The unique representation of xi belonging to L as linear combination of vectors belonging to the basis B is xi is equal to 0 into x1 plus 0 into x2 plus and so on 1 into xi. Okay, at ith place scalar is 1 and other 0. That is here 0 into x1 plus 0 into x2 plus and so on 1 xi plus 0 into xi plus 1 plus and so on 0 into xn. Therefore, according to our definition of f, we can write f of xi is equal to 0 as scalar, 1 as scalar. So we can write f of xi is equal to 0 into f of x1 plus 0 into f of x2 plus and so on 1 into f of xi plus 0 into f of xi plus 1 and so on plus 0 into f of xn. That is f xi is equal to gamma I. So it can be written as f of xi is equal to 0 into gamma 1 plus 0 into gamma 2 plus and so on 1 into gamma I plus 0 into gamma I plus 1 plus and so on 0 into gamma n. That is f of xi is equal to gamma I is equal to 1, 2 and so on. Now we shall show that f is linear functional. Let AB is the element of f and xy is the element of L. Let x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. And y is equal to beta 1 x1 plus beta 2 x2 plus and so on beta n xn. then f of ax plus by is equal to f of a, putting the value of x here, plus by. Okay, y is this one, so we can write this. So f of a alpha 1 x1, a alpha 2 x2, and so on, plus a alpha n xn, plus b beta 1 x1 plus b beta 2 x2, plus and so on, b beta n xn. So this one, f of a alpha 1 x1 and b beta 1 x1, plus second term a alpha 2 x2 and second term of this b beta 2 x2. Okay, plus and so on. Last term a alpha n xn plus b beta n xn. So x1 common here, a alpha 1 plus b beta 1 x1. Okay, this plus this. Second term a alpha 2 x2, b beta 2 x2. So with common we can write a alpha 2 plus b beta 2 x2, plus and so on. Last term with common xn, this term plus this term can be written as this. So f of this term, so a alpha 1 plus b beta 1, a alpha 2 plus b beta 2, and so on, a alpha n, b beta n are scalar. So this expression can be written as a alpha 1 plus b beta 1 f of x1, a alpha 2 plus b beta 2 f of x2, plus and so on, a alpha n plus b beta n f of xn. So f xi is equal to gamma I, that is f of x1 is equal to gamma 1, f of x2 is equal to gamma 2, and f of xn is equal to gamma n. So this expression can be written as a alpha 1 plus b beta 1 into gamma 1, a alpha 2 plus b beta 2 into gamma 2, plus and so on, a alpha n plus b beta n into gamma n. Okay, so multiplying in both term gamma 1 and this two term, multiplying gamma 2 plus and so on, in this term we multiply gamma n. We have a alpha 1 gamma 1 plus b beta 1 gamma 1, a alpha 2 gamma 2 plus b beta 2 gamma 2, plus and so on, a alpha n gamma n plus b beta n gamma n. Okay, so we can write this is in two terms as a alpha 1 gamma 1 plus a alpha 2 gamma 2, plus and so on, a alpha n gamma n, and second term as b beta 1 gamma 1 plus b beta 2 gamma 2, plus and so on, b beta n gamma n. Okay, so a common in this term and b common on this term. So we have a common alpha 1 gamma 1 plus alpha 2 gamma 2, plus and so on, alpha n gamma n, plus b common beta 1 gamma 1 plus beta 2 gamma 2, plus and so on, beta n gamma n. So as per this we can write here a into fx plus b into f of y. So f of ax plus by is equal to a into fx plus b into fy. Therefore f is linear functional on L. Thus there exists a linear functional f on L such that fx I is equal to gamma I for I is equal to 1 to n. Uniqueness of f. Let g be a linear functional on L such that gxi is equal to gamma I is equal to 1 to n for any vector x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on, alpha n xn belonging to L. We have gx is equal to g of alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. This can be written as alpha 1 gx1 plus alpha 2 gx2 plus and so on alpha n gxn, because g is linear. So this can be written as alpha 1 gamma 1 plus alpha 2 gamma 2 plus and so on alpha n gamma n by the definition of g. Here g xi is equal to gamma I. Okay. So by the definition of f, this can be written as f of x, because f of x here, this one is fx. Okay. So gx is equal to fx. Thus gx is equal to fx for all x belonging to L. Therefore g is equal to f and f is unique. Next theorem. Let B, x1, x2 and so on xn be a basis for n-dimensional linear space L over the field F. Then there is uniquely generated basis B star, F1, F2 and so on Fn for L star, such that Fixj equal to delta Ij, that is Kronecker delta. Okay, Kronecker delta, that is value of delta Ij is equal to 1 if I is equal to j and 0 if I not equal to j. So Fixj is defined as Kronecker delta, that is delta Ij, I and j equal to 1 to n. Consequently, the algebraic dual of n-dimensional space is n-dimensional. The basis B star is called the dual basis of B. Proof: B is equal to x1, x2 and so on xn is an ordered basis for L. Therefore, by the above theorem 1, this theorem, there exists a unique linear functional f1 on L such that f1 x1 is equal to 1, f1 x2 is equal to 0 and so on fn xn is equal to 0. That is Fixj. Okay, if I and j equal, that is 1, and I and j different, that is 0. Okay, where 1 0 0 0 is an ordered basis set of n scalar. Okay, here f1, f2 and so on fn. So this is unique functional on L. Okay, as discussed in above theorem 1. In fact, for each I is equal to 1 to n, there exists a unique linear functional fi on L such that Fixz, that is 0 and 1, if I not equal to j and I equal to j respectively. That is Fixj is equal to Kronecker delta Ij. Okay. Let B star is f1, f2 and so on fn. Then B star is subset of L star containing n element of L star. We shall show that B star is a basis for L star. First, we shall show that B star is linearly independent and generates the span. So first we shall show that B star is linearly independent. Let C1 F1 plus C2 F2 plus and so on Cn Fn is equal to 0. 0 means that is 0 vector of L star. This implies that C1 F1 plus C2 F2 plus and so on Cn Fn x equal to 0x. Okay, so this can be written as C1 F1x plus C2 F2x plus and so on Cn Fnx equal to 0. that is summation I is equal to 1 to n ci fi x is equal to 0. This implies that summation I is equal to 1 to n ci fi xj is equal to 0, j is equal to 1, 2 and so on, n. Putting here x is equal to xj. Okay. So fi xj as Kronecker delta ij. So this implies that summation I is equal to 1 to n ci delta ij is equal to 0. This implies that cj is equal to 0, j is equal to 1, 2 and so on, n. We expand this, okay. I is equal to 1 to n, that is c1 delta 1j plus c2 delta 2j plus and so on, cj delta jj plus and so on, cn delta nj. Okay. So here we have one term cj delta jj. Okay. So delta jj 1. So we have cj equal to 0, that is cj is equal to 0 and j is 1 to n. This implies that f1, f2 and so on fn is linearly independent. Now we shall show that B star generates L star. Let f be any element of L star. The linear functional f will be completely generated if we define it on a basis for L. So let f xi is equal to ai. We shall show that f is equal to a1 f1 plus and so on an fn, that is summation I is equal to 1 to n ai fi. Okay. Let x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn equal to summation j is equal to 1 to n alpha j xj. Be any element of L. We have f of x is equal to f of this term, okay, and f is functional, so we can write alpha 1 f of x1, alpha 2 f of x2 plus and so on alpha n f of xn, okay, because f is linear. F of x1, that is a1 by this plus alpha 2 a2 plus and so on alpha n an. Also a1 f1 plus a2 f2 plus and so on an fn x equal to a1 f1x plus a2 f2x plus and so on an fn x. Okay, this can be written as summation I is equal to 1 to n ai fi x equal to summation I is equal to 1 to n ai fi, putting the value of x here. X is this one, summation j is equal to 1 to n alpha j xj. Okay, so we have written here. Fi is linear functional, so it can be written as summation j is equal to 1 to n alpha j fi xj. Okay, so this term can be written as summation I is equal to 1 to n ai j is equal to 1 to n alpha j, and value of this is Kronecker delta ij from equation 1. Okay, value of this is alpha j. Okay, because if I and j equal, then del ij is equal to 1, otherwise 0. So we have here if j is equal to I, so this is ai alpha I. So summation I is equal to 1 to n ai alpha I. Value of this equal to a1 alpha 1 plus a2 alpha 2 plus and so on an alpha n, that is fx from equation 2. Okay, Thus, we have fx is equal to a1 f1 plus a2 f2 plus and so on an fn x for all x belonging to L. Therefore, f is equal to a1 f1 plus a2 f2 plus and so on an fn. That is, every element f in L star can be expressed as linear combination of f1, f2 and so on fn. Therefore, B star spans L star. Hence, B star is a basis for L star. Now, dimension L star is equal to number of distinct elements of B star is equal to n. Corollary: if L is an n-dimensional linear space over the field F, then L is isomorphic to its algebraic dual L star. Proof: we have dimension L star is equal to dimension L is equal to n, therefore L is isomorphic to L star. In this lecture, we have discussed the linear functional, dual vector space and dual basis. These are the references have been used in this lecture. Function analysis, Dover publication written by George Beckman and Lawrence Naresy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.